Here is a sleazy trick involving fractional derivatives. But first, what is a fractional derivative? When you differentiate a function again and again, you write stuff like this. What if n is generalized to any real number, not just integers? That's a fractional derivative. An important special case is the semi-derivative. It's an operator that, when applied twice, gives the same result as a normal derivative. There are several ways to define the fractional derivative. Here we will look at two simple approaches. One way, look at how derivatives affect sines and cosines, or exponential functions. It's obvious how to generalize n from an integer to any real number r, or even to complex numbers. Any function that can be described as a sum of exponentials, sines or cosines, can be fractionally differentiated using this definition. The other definition, let's look at powers of x. One derivative, the second derivative. This will get messy, so let's define a symbol, pi, defined like this. Now we can write, oh, this looks easy. This is easily generalized to any real order r and even to complex orders. An important detail to note is that pi subscript any negative integer is 0. Do these two approaches to defining fractional derivatives give the same result? I say yes. Here's how I argue it. First, observe that if we write the exponential function like this, as seen in every calculus textbook, and we use our pi symbol, then we have, as the arbitrary order fractional derivative, this. What can we say about this? Let's give it a name. I'll pick xi for no particular reason. Can we understand xi in terms of familiar functions? What properties does it have? The derivative of xi, just a plain single derivative, is this. Now we have a differential equation for xi. Have fun with that. It's nothing too tricky or difficult, but with that extra term dangling off the end, I think it's ugly. But what if we do this? Now the sum goes from negative infinity to infinity. Remember that pi subscript any negative integer works out to 0, so this sum does not appear to be any different from before. Let's give this a name. I'll choose, for no particular reason, capital E. The arbitrary order fractional derivative of this is. What can we say about this function? Let's differentiate it once to see what happens. This is different from before. Differentiating is identical to not differentiating. It's only a relabeling of terms. There's only one function that satisfies this simple differential equation, and that is the exponential function. So we conclude now, one thing I left out is that parameter a I had at the start, and I left it out. I'll leave it to you to work out the equations, including that if you like. But spoiler alert, there are no surprises. So, my fast and loose conclusions are 1. The two ways of defining a fractional derivative, as shown, are identical. And 2. Adding an infinite number of zeros to an infinite series does matter.